Thank you, Khaled,
Thank you.
for a very informative presentation. I think for the sake of time, we'll move to Denelli. Denelli's going to give us two different presentations. And Denelli Zaccaria is an associate professor and agricultural water management specialist in the Department of Land, Air, and Water Resources at UC Davis. And he comes to us with a extensive international and national experience. He's been a member of the faculty at UC Davis since 2013. And his expertise and current work focuses on irrigation management, determination of crop evapotranspiration, water productivity, mitigation of drought, etc. So with that, I'll turn it over to you, Denelli.
Thank you so much, Marilu, and thank you all for having me here today. I'm sharing my screen, and I hope you can see my presentation now. Can you see it?
Yes, we can.
All right. Okay. I was asked to give a presentation on method and technologies for scheduling irrigation in avocado. And so I prepared a few slides. This is general in scope, but there is some specific reference to the challenges of irrigation of avocado. We all know that it's not an easy task, and maybe it's a little bit more complicated for a different reason with respect to other permanent crops. In any case, I wanted to keep this, again, a little bit general in scope in order to give you an overview of what is irrigation scheduling, and then we'll provide some specific reference to irrigation management of avocado. So irrigation scheduling in general provides answer to three main questions. Normally is referred to providing answer to two main questions, but with micro irrigation and planting on marginal soils, there are other considerations to take. So the first question is when to irrigate our crops. In the old school book, normally say before the three-phase water deficit, but with micro irrigation and with fruit crops, high-value fruit crops, there also some practices that somehow are aimed to improve the fruit quality. This is not the case of really the case of avocado, but this is the case of citrus and other pistachio and other permanent crops. So we can say that we have to irrigate our crops before the three-phase water deficit or a specific deficit or stress level that we want to maintain, which are beneficial for fruit yield and quality. Think about wine grapes, for instance, or other high-value crop that might get some benefit for fruit quality of partial irrigation. The second question is how much water to apply, and again, the old school books will say the amount of water used by the trees for evaporation and transpiration since the last irrigation or rainfall event. And when we come to the fruit quality and fruit high value production, we can say also that we can irrigate a portion of that ET that allows us to maintain some target of water stress or mild deficit in order to improve quality. The third question, which is never actually considered in the old school irrigation scheduling, how do we best apply the necessary amount of water? So once we decided the timing and the amount of water, then it comes to how to apply in the best way that necessary amount of water. So we can apply uniformly or site specifically depending on the soil hydraulic characteristics, or we can have at least two different practices like frequent light application or infrequent deep irrigation. And again, this is not the case of avocado because of the specific root system. But we can also apply water at a rate and volumes that are compatible with the soil infiltration rate and the water holding capacity. And now with the energy crisis and with the high cost of fuel, we have also to care about energy rates and the energy cost, and try to avoid, as Khaled mentioned, the time of use, the high peak energy rates. So this, high peak energy rates made us modify the design criteria for microirrigation. Now, there are three main methods for scheduling irrigation. One is what is called weather-based or evapotranspiration-based. The second one is soil moisture-based. And the third one is plant-based. Those are three pillars, and those are alternative irrigation scheduling method, but we can also combine those in different ways. The first one, the weather-based, is so we need to estimate or measure crop ET and apply water accordingly, to refill what the crop has used. It's very common. It's been very common in California for many different crops in the past. It's still very much used, but requires some data and information, as Khaled has mentioned, and also the calculation. So calculations sometimes become a little bit tricky, especially when we have micro-irrigation or drip irrigation. The second one is a soil-based, and we have to appraise the soil water status on a regular basis or continuously. It's equipment intensive because we have to have sensor and communication in the field, and we all know that technology work when it works, and sometimes it gets disconnected, or it gets broken, it gets damaged, and so the fact of having equipment in the field is somehow requires a lot of attention in troubleshooting and maintenance. But anyway, it's a good method for periodic check and also for feedback of when we use other type of irrigation scheduling. The third one is a little bit more advanced and is based on the plant, what the plant feels. We all know that the plant integrates what it feels in the soil, what it feels in the area or in the atmosphere around the canopy. And so if we monitor the plant, this is probably the most integrated and advanced way, because our goal is to, supply enough water to avoid water stress or to avoid excessive water stress. So this method, the plant-based, requires that we detect the plant water status on a regular basis or on a continuous monitoring basis. Is labor intensive because it requires quite a bit of work, especially with some specific technology. And it's also well developed for some crop like almonds and grapes, but not for all the crops. And so in some cases, it requires some fine tuning and some calibration. In all cases, all the irrigation scheduling methods, when we have micro irrigation in the field, requires skilled personnel on the farm and also high capacity for executing whatever schedule we come up with, and also for fast troubleshooting. So it's not only the fact of deploying high-tech type of irrigation, but having people on the field and personnel that is able to troubleshoot and execute what we plan to do in order to irrigate our crops. So this high-tech irrigation requires a lot of training and a lot of education of the farm personnel as well. Now, the weather-based, starting from the weather-based, the criteria is to replenish the root zone with the water amounts that has been lost by soil evaporation and crop transpiration since the last irrigation or rainfall event. As Khaled has mentioned, in California, we estimate the consumptive water use or crop evapotranspiration by multiplying reference ET, which is related to grass, by a crop adjustment coefficient that tells us our crop, how much water our crop takes with respect to grass. So a surface of grass is our reference, but it has to be, kept without any water stress, without any nutritional impairment or shortage and without any water shortages. And if we have good value of crop coefficient, we can convert this grass ET into crop ET. There are three alternatives here. We can use historical ET average. It could be historical reference ET or historical crop ET in case we have it for the specific crops. Or we can use real-time reference ET, and then we multiply by crop coefficient values. Or we can use forecast ET, and we multiply by crop coefficient value. In any case, what we really need in terms of high quality information is accurate crop coefficient values. Those are always crucial. Now, in real time ET, this is what we call it explain. The reference ET part is provided in California by the CIMIS, the California Irrigation Management Information System. And then if we have good value of crop coefficient, then we can combine the two in order to determine or estimate the potential crop evapotranspiration. Now, there are other sources of information, and I'll explain this in a second segment. And this is a FRET, Forecast ET from the National Weather Service. So I will not spend a lot of time, but you can have information on the next 7 days, 1 to 7 days ahead in order to plan your water delivery from the district or your water application from the well. And this is a very interesting tool for improving also the water and energy use. I have to mention also that the Avocado source put together an irrigation scheduling calculator. This was pointed out by Mary Lou Paya to me. I'm sorry, I haven't worked so much on avocado in California, but I work on avocado in Chile in a past couple of years. But I saw this is a very comprehensive scheduling calculator that helps people on the ground to get a sense of the real amount of water they have to apply in gallons. Avoiding all the intermediate calculation. As you can see, there's a crop coefficient source, and that there's also data source on reference evapotranspiration. There's a distribution uniformity that you can put here, surface area under the tree canopy, and application rate by the different emitters. So this is pretty comprehensive calculator that helps get a sense of the amount of water that you have to apply along the crop season. And so it's a very valuable tool. And as I heard it's used also in many other parts of the world, but it was developed by Avocado Source and for California Avocado. Now, the drawbacks of ET-based irrigation scheduling is that, when we talk about ET crop or crop coefficient, we talk about something that is supposed to be well water, without any nutrient limitation, without any shortage of water, without any other source of stress. It could be salinity, sodicity, or hypoxia. So, using generalized crop coefficient that refer to ideal condition might lead you to an estimate of the amount of water to apply. That could be very different from the actual evapotranspiration of your site-specific orchard. So what I'm trying to say is this is a good method for estimating and planning ahead, but you need to tailor things to your site-specific conditions, and that means basically that the amount of water that is consumptively used by your orchard depends on the canopy volume, depends on the planting density, depend on the height of the tree, depend on the row orientation, and also the slope and aspect. So you might run the risk by applying water estimated through this generalized crop coefficient. You might run the risk of over-irrigating or under-irrigating. And so there's also another point. Most of the available crop coefficient information now was developed during the 80s and 90s for infrequent irrigation methods like surface irrigation or sprinkler irrigation. And this is generally for all the crops, and was developed for well-drained soil and flat ground, so ideal condition, but also for varieties, rootstock, planting density, canopy management practices. They were quite different from the current ones, and in most of the cases, the crop coefficient refer to ideal condition of the past, were conducive to lower yields per acre that we currently have. So just to give you an example, think about a normal planting versus a high density planting. I'm not sure this is going to use the same amount of water, one type of orchard versus the other. So we need to tailor our estimation to the site-specific condition of our orchard. In addition to that, micro-irrigation is really a game changer because we actually spoon feed water and nutrient to trees, and so we have healthier trees that normally use more water than with respect to infrequent irrigation. And so healthier trees develop a better canopy, have a better light interception, and if we do a good job with the scheduling and management of irrigation, this will provide ideal condition for tree water use. So what I'm trying to say here is that looking only at the ET or evapotranspiration might be limiting for high value food production. So we need to look also at the soil and the tree water status in order to schedule and optimize our irrigation management. There's also another case, and instead of estimating our crop water use, we measure it. So this is we measure the actual evapotranspiration in the site-specific condition of our orchard. This is a first picture is an example of our research scale measurement equipment for ET, for actual ET, and this measure fluxes and energy in the site-specific condition. So we have the actual ET, so our job is simplified because we just need to replenish what the measurement device sends. This is another example, what Khaled mentioned, it is the Thule system, which is a measurement device that, kind of a commercial development from a research scale type of equipment. But also we have audible mark, like in the other picture, and Ben Faber is also some of this thermometer. There are probably more suitable for field crops like corn, soybean in the Midwest. But they give you some measurement, and then it's a matter of fine tuning the amount of water measured to the actual site-specific condition of your orchard. Now, moving to the second method, this is a soil moisture based irrigation scheduling. It consists of 3 steps: observe the soil moisture frequently or monitoring the soil moisture in continuous mode, and then start irrigation at certain target level of soil moisture, or we call it management allowable depletion. So we allow the soil to deplete some of that soil moisture, and then a certain threshold before we hit the water stress, then we refill to the maximum capacity. And then we can stop irrigation when the soil moisture reach some target level. This graph is an example of watermarks that we normally use in many different crops. It's a simple tool, and we can set the watermarks at different depth. This is I think is a practical example, refer either to citrus or to pistachio, but you can see from the different sensor at different depth in this graph that most of the water use happens between 24 and 12 inches deep into the soil. The soil moisture sensor at 48 inches is basically showing no depletion or just a slow trend of soil water depletion. It's important to notice that these are point measurements, so they're really refer to where you put your sensor, and those are somehow have to be taken with a pinch of salt because because not all the soils are uniform, not all the orchards are uniform. So a preliminary assessment of the spatial variability of soil is needed before you deploy the soil moisture sensor, because you have to target some critical areas. If the soil in the orchard is somehow homogeneous or uniform, then it doesn't really matter where you put it. But this are kind of a sophistication that become very relevant in when the new orchards are planted on marginal soils or highly variable soils. Now, this, as you probably know, the soil moisture can be measured in terms of content. The soil moisture content could be percentage, or it could be expressed in terms of inches of water per foot of soil, or millimeter of water per meter of soil. And basically, the soil moisture content will tell you how much water is available per unit of soil. It could be percentage in weight, percentage in volume. But normally on a practical level, we use the inches of water per foot of soil, and that's the most common and practical way. But also we can measure the soil moisture tension, or the soil moisture potential, or soil matrix potential. And this is in terms of negative pressure. So this expresses the amount of energy that the plant has to deploy to extract water from the soil. So it is expressed in centibar or kilopascal. So it tells you how strongly water is held by soil particle. The higher the tension, so the more negative is the number, the drier is the soil, and the more difficult it is for the trees to extract water. And these are two schematics that will show you, especially 5 kilopascal on this graph is definitely more water, express more water availability than 30 kilopascal, because all this are basically negative measures. So tension means negative pressure. And so 150 kilopascal basically it showed that the soil is very dry and it's very difficult for the plant to extract water from the soil particle. Now, there are a few challenges on scheduling and managing irrigation in avocado. First of all, if well-fed, our avocado trees are heavy water users. So if they are properly irrigated, they can uptake and use 40-50 acre range per acre per year of water. Part of it can come from other sources. On the coast, it can come from soil moisture. From moisture that comes from fog and dew, but also it comes from rain. But avocado. It's a heavy water user. There's another point that almost a large part of the feeder roots, so the fine roots, are basically concentrated in the top 8 to 10 inches of soil, and those roots are the primary absorbers of water and nutrients. So there's also another point that avocado roots are not very efficient in uptaking water, although everything is concentrated in the topsoil, but the feeder, so the fine roots have few or no hair, so they're not able to search and scout and extract water that is held tightly by soil particle. So as a rule of thumb, below minus 25 kilopascals, avocado trees roots are not really able to extract a lot of water from the soil. Avocado is also a low tolerance to salinity, but also very low tolerance to hypoxia, so to lack of oxygen. And so on one side, we have to supply some extra water to leach the salt in order to keep the soil salinity low. But also we have to make sure that extra water is well drained in order to flush the salt away, because otherwise water logging and low oxygen will impair root growth and also leaf health. So the other point is many avocado orchards are planted on steep hillside with loose soil, and those are either decomposed granite or sandy loam soils. And those are at high infiltration rate, but they do not retain and store water well. And so that means that whatever is the amount of water that we have to apply, we have to be very careful with the frequency. So the result of all this consideration is that moderate water stress can onset easily on avocado orchards and greatly reduce yield. So some work done in South Africa show that the recommendation is that soil water potential, so I mean the soil water tension should not go below, should not go more negative than 25 to 30 kilopascal in sandy soil and minus 35 kilopascal in clay soil. And those are, you know, very conservative recommendations. Now, this is this table will show different soil moisture measurement device, tensiometer, granular matrix, capacitance, time domain transmissivity, and time domain reflectivity. The last two type of sensors are mainly used for and deployed for research purposes, but there are also commercial version of the TDR and TDT, and those are pretty reliable. But the most widely used are tensiometer, granular matrix, and capacitance probe. And you can see that the different feature in terms of soil moisture, soil volume measured, sensitivity to our gaps, and sensitivity to salinity. So this will give you an idea what to use in the different types of soil. Tensiometer and granular matrix sensor, or watermarks, for those are an example of a granular matrix sensor. They measure the soil water potential or moisture tension. The other measure volumetric water content, and that's expressed, as I mentioned, as a volume of liquid per unit of volume of soil, or millimeter of water per meter of soil, or inches of water per foot of soil. Now, this is a quick drawing of that shows the kind of a root distribution in flat orchard, or root distribution in hillside orchard, and you can see there, very dense concentration of roots in the top layers. And this graph will show you the relative root abundance with with depth of soil. And this is for mandarin, but the same concept applies for micro-irrigated avocado orchard. You can see as you go deeper and deeper, the root abundance and the uptake in root abundance is decreasing, so that it makes no point to try to measure deeper than probably 30-40 inches of soil in subtropical crops. Now, for micro-irrigated orchards, avocado orchards, I would say 2 to 3 sensors installed at the depth of between 8 and 10 and 18 to 20 are probably sufficient. The most critical one is the shallow, but the other one, the deeper, will tell you when a certain soil moisture tension is reached, you can stop irrigation. So the deeper is for collecting feedback on your irrigation management. This is just a schematic that show a similar situation for this is for wine grapes, but I use this just to show kind of a setup with 2 or 3 watermarks and a data logger that can be connected with the cloud. For instance, this is a device that a trellis system is using watermark, but you don't need to physically store the information here at the orchard. The information can be sent to the cloud, and you can check your soil moisture from far away. And this is another setup where we have salinity into the soil, and so the watermark might be sensitive to a certain value of salinity. So beyond, higher than 4 decisiemens per meter, the reading of the watermark can be biased and can be unreliable. This is the reason why we normally put also tensiometer in saline and solid soil. But this is not a deployment or an application of pistachio. Irrigation frequency is also pretty important. And so in pistachio for all the consideration that we talked about. In the coarse texture soils that are well drained. So daily light application using either drip or micro sprinkler could be appropriate. And in heavier texture soils, and those are you know, a little bit more clay into the soil mix, those can suffer some anaerobic condition or hypoxia. Irrigating every 2-3 days is desirable. Some research was conducted in Chile that shows that allowing 50 to 60% of the total soil water to deplete between irrigation did not really affect yield or fruit size relative to more frequent water application. However, as a conservative number, a conservative threshold, I would say 25 to 30% soil moisture depletion are adequate for most soil to maintain a good supply of water to the roots and good supply of oxygen to the roots. Those tables. The table here on the left will show you the soil moisture content reading that you should get at this value of 50% of the plant available water for different type of soil texture. So those are just to give you some threshold where you should probably irrigate if you have a loamy sand or sandy loam soil. And the second table here will show you the same 50% of plant available water, but this is expressed in soil moisture tension in case you use tensiometers or you use a watermark. And those are threshold value that, threshold value you consider for scheduling your irrigation for the different type of soil. The benefit of scheduling irrigation based on soil moisture, those are, I would say, this method is suitable for irrigation of young trees and immature stand because you know, you prevent any water stress and excess water, so you can promote a fast canopy development and fast onset of fruit production. So it helps achieve kind of an adequate root growth, and that is important to buffer for heat waves and drought periods or extremely dry period. But also is important to avoid excessive irrigation, so with overwatering, and that will cause hypoxia, and also if you have good drainage, some nutrient leaching. Also, it's important to avoid favorable condition to pest and fungal disease like Phytophthora. This is a picture of a citrus tree with the fungal disease of Phytophthora. Now, there's also some drawbacks of soil moisture-based irrigation scheduling. So monitoring soil water status will only give you an indirect estimate of your plant water conditions. This is an example that we had in pistachio. You can see the watermarks at 3 different depths, 18, 36, and 48 inches. All the watermarks were showing well water condition, but the trees were stressed anyway, even if the soil moisture was showing well water condition. This was the case of salinity and sodicity impact on the soil feature. And you can have hypoxia, you can have hard pans or compaction layer that will not allow the roots to thrive in ideal oxygen condition. There was also some soil water infiltration problem because the top soil was showing good amount of water, but the deeper soil were completely dry. And this is how the trees look like in the soil saline sodic orchard and pistachio. So in order to tailor your irrigation management, you really have to look not only at the ET and soil, but also look at the plants and how the plant look, and and do some plant-based measurement. There's also some other problem with micro irrigation. There might be some preferential water flows, and this is what is showed in the picture. So you see the topsoil is pretty homogeneous, and then there's cracks, and so you get subsurface percolation because of the cracks, and the same stuff is shown in the picture on the right. And this happens when the soil is layered and is not being prepared adequately for planting the orchard. So soil moisture can be used as a feedback information after irrigation. Now, imagine you put the sensor in a dry area. That sensor will tell you that the soil is somehow dry. It will keep irrigating, and probably you'll create some water logging in the topsoil layer. So this is not necessarily the right way of managing irrigation in this kind of marginal soil. So we need to look also at the plant water status besides the available soil moisture. There are several methods to monitor the tree water status and the stress. Probably the most widely used is either leaf or stem water potential measurement. The second one could be sap flow. And another one could be canopy temperature, so measuring the temperature of the canopy with respect to the air temperature. So what happens if the plant is stressed is that the canopy receives a lot of energy from sun. It cannot dissipate this energy through transpiration, and so it increases temperature. So when the canopy is transpiring well and the plant is well watered, if you touch the leaf, they will be cooler than the air temperature. And this is a method that my grandpa used for scheduling irrigation in grapes. But now we have tools that will, with digital thermometer or infrared thermometer can monitor this canopy temperature. If the temperature of the canopy is very similar to the air temperature, there is some problem there. There's not sufficient water, or there's excessive water, because the plant, even when it's under hypoxia or lack of oxygen, will close the stomata. It will not transpire water, and so it will increase its temperature. I'm pretty sure you're all familiar with the pressure chamber, or in order to measure the leaf and stem water potential. But this is a pressure chamber where you insert the leaf and you increase the entrance of gas, and so you observe whether bubble comes out of the petiole. For the avocado, this information was taken from the FAO Irrigation and Drainage Handbook on Crop Year Response to Water. This was published in 2012. In the FAO Handbook number 66 indicate that midday stem water potential above, so less negative than minus 0.3 to 0.5 megapascal, indicate for avocado the absence of water stress during sensitive stages like flowering and fruit set. On a normal, typical summer day, well-watered trees will have minus 0.5 to minus 0.6 megapascal of midday stem water potential, and this is for reference ET of about 1/4 of an inch to 0.30 inches. In stem water potential between minus 0.6 and minus 1 megapascal are indicative of mild to moderate stress, and this can extend to minus 1.5 to minus 2. So more severe water deficits are indicated by stem water potentials more negative than 1.0 megapascal, so reaching either 1.5 or 2 megapascal. So those are threshold of stem water potential if you want to apply this method for scheduling the timing and the amount of water application. There are other tools that are less time consuming and less labor intensive. There are dendrometers and other plant sensors. This is an example of a dendrometer. Those are devices that measure the shrinking and swelling of the trunk or the stem, and those are micro movement. The more the plant is stressed or water stressed, the higher is the fluctuation between shrinking and swelling. And those are tools that can be used on a continuous basis, and on a, those are monitoring device for somehow detecting the occurrence of plant water stress. This is an infrared thermometer. I use this quite extensively in citrus. Because subtropical crop like citrus and avocado, they close the stomata pretty early in the morning, around 8 a.m. during spring and summer. And so their temperature increase, but there's a kind of a signature, dynamic signature. And then they reopen the stomata around 6 or 7 p.m. as the temperature drops. There's also some other plant sensor. They're called ZIM probes, and those are basically a sensor that are leaf tensiometers. So they feel the water content in the leaf tissues, and they will provide information on a continuous basis. There's also sensor bark tensiometer. Those are the Flora Pulse bark tensiometer. This is a technology that is being applied in almonds and walnuts and pistachio. But all this new sensor and technology, they somehow require some fine tuning and validation versus some more solid measurement like stem water potential or leaf water potential. Those are fruit dendrometers are normally used to measure the growth of the fruit. They can be used on target fruits or on critical fruits, and these are also kind of a later version that are used on other subtropical crops like oranges and mandarins. Sorry, this is a double slide. I forgot to cancel. But I just wanted to point out. Let me restart this presentation. 1 second. The last couple of slides I wanted to show you. In terms of deficit irrigation strategies in avocado, we all know that we have a drought since a couple of years, and along the coast there's also this regulatory problems with groundwater pumping. So water is becoming more expensive, and so we all have somehow the aim of reducing the water use. But all the experimental evidence so far indicate that regulated deficit irrigation is really not a recommendable practice for irrigation of avocado, because avocado is highly sensitive to water deficit. And also, if you apply less than what the avocado requires, there's also there will be salinity build up into the soil that will require some leaching. And this is valid for most of the irrigation season. At the same time, excess irrigation is highly detrimental because of the sensitivity to waterlogging, hypoxia, and also high risk of fungal disease infection like Phytophthora. So probably the best irrigation practice will be for avocados. So it should be based on supplying the amount of water that is used by the tree, and supply that amount at the optimal interval to prevent water deficit, and at the same time to supply adequate oxygen to the root system. With that, I think my presentation. Oh, last slide. There's also a combination of different approach. This is my very last slide, and those combination of different approach. So you can decide the irrigation timing based on plant-based, either stem water potential or other continuous monitoring of plant water status. This is perfect for the proper irrigation timing. And then you can use weather-based or ET-based for determining the adequate irrigation amounts. And then finally, you can get soil-based feedback and also check for feedback from the flow meter, like Kali was pointing out. With that, I apologize if I spelled over and exceeded the time that was allocated to me, and I'll stop here. Thank you.
So Danilo, do you want to give a shortened version of the FRET, or?
Yes, I can fly quickly on the thread and focus on the most important part. If you think is needed, yes, I can do it.
I think, well, we're at 9:30, so maybe the thing to do would be, let me ask you this, would you be willing to sit in Zoom and record that presentation for us, and then we can post it?
Yes, I can do that.